Hello and welcome to our first installment of our last unit, 13. I hope it's the last one, Air and Sea Interaction. And this pictorial was determined by the fact that we actually have different climates on the planet. We have equatorial, which you see is right around where the equator is located, a little bit north and a little bit south, depending on season, but that's where we actually have these tropical rainforests. And then we have the tropical area where we also have tropical rainforests, so everywhere in between there we actually have really nice lush vegetation uh, on the land. Subtropical location of our deserts in both hemispheres. Then we move to temperate, where we actually have the forested areas, and we move to polar, our subpolar and polar, where we actually have taiga and tundra type environments, including all of Antarctica and all of the Arctic Ocean up there. This icon is going to be where I want my kids to draw in color. So when you see this again, I'd like you to draw and I'll explain what that is later. Okay, so oceans of air and water. Atmosphere and ocean is one interconnected system. Changes in atmosphere affects the ocean. Changes in the ocean affect the atmosphere, and both have waves and are very fluid-like. The ocean without any problem, without any doubt, but the atmospheric layer actually also acts like a fluid. There are waves, there are internal waves, external waves, there's wavelengths and whatever. An example of that are actually this picture right here, and it looks like something is taking the air, which is moving pretty linearly, and actually making waves out of it. And what's going on is we actually have wind moving over a mountain range, and these are mountain peaks that are sticking up, and they're actually causing a disruption in the wave of air, and it goes up and we get clouds, it comes down and we get no clouds. So you can see clouds and no clouds, and it continues for a long fashion, getting weaker and weaker with time, and eventually it'll go back into a linear flow. It's all caused by unequal solar heating. The equator receives a lot more direct sunlight. If you take a look at how much area is actually in this sun ray over how much is here, it's a lot lower, a lot smaller amount here. So not only does it get more solar radiation, it actually gets it for more time during the day. So low latitudes closer to the equator receive more direct solar radiation as well as more hours during the day, and higher receives less direct and lesser amounts during the day. Also is going to be affected by seasons, and I'll show that to you actually relatively soon. If we talk about solar radiation, we get 100% of the atmospheric solar radiation hitting our atmosphere. You can see 3% is absorbed by an upper layer of the atmosphere. Others come in there, gets diffused and reflected by dust and things in the atmosphere, or clouds in the atmosphere, or actually the gases in the atmosphere. Some makes it all the way down to the earth and heats up the planet. That's 25%. Some has hit the surface and reflected back. Some actually from this atmospheric diffusion and reflection actually comes down. So we pick up, looks like about 45% of the solar radiation. That means a whole lot more goes up. Albedo is how much does of the sunlight does the Earth bounce back. And then if we go on to the next one, of that 21% of it actually goes right back into the atmosphere. 45% moves over here. We get some moving up as latent heat. We get some moving up as convection. We get some of moving up as greenhouse, and some direct loss. And if we go up, we actually see that 3% that was right there radiates back out, and we get 31% bouncing off, and we get 69% re-radiated back into space as long wave radiation. And if you add those up, there's the 100% that comes in and 100% goes out. And we want that it's a budget. We want that to stay. We don't want the Earth to heat up. We don't want it to cool down. The problem is when we actually take these gases and make more greenhouse gases, more will actually be absorbed and less will be radiated out into space. And that's greenhouse effect. We need some greenhouse effect, otherwise we're a lot colder at night and a lot warmer during the day. We do need some greenhouse, but we'd like it to keep the same way it is right now. Equatorial areas receive excess heat. So if you take a look at the areas that are located between 23.5, actually they're going up to like the high 30s and low 30s. We actually gain more energy than we lose. And then you go up above that and they actually lose more than they gain. And what happens is the heat moves up toward the North Pole and down towards the South Pole, which cools off the polar areas and warms up the, cools off the tropical areas and warms up the polar areas. And these are calories per square centimeter per minute, and not very many calories, but it all adds up. Insulation factors, latitude. The lower the latitude, the higher insulation you're going to get. Thicker the atmosphere. The atmosphere towards the pole is not as thick as it is during the tropics, and that has to do with the expansion due to temperature. But it's actually a lot, about 2 to 3 times higher at the equator than it is at the poles. It's a lot thicker atmosphere up here. Albedo, sunlight bounces, or snow bounces back almost 100% of the light, where dark roads reflect almost nothing, and they heat up. That's the reason why if you go from a sidewalk to asphalt barefoot, it's a lot warmer during the summer and a lot cooler on the concrete or the grass. So different amounts. Moon has a very high albedo. It only receives about 6 to 8%. Snow bounces back a whole bunch. Crops, grassland, asphalt. You actually see a whole bunch of stuff out there. Time of day, more sunlight during the daytime than at nighttime, and vegetation versus bare rock. Vegetation actually absorbs quite a bit. Bare rock, depending on the color, can absorb or reflect it. This is another shock wave, which you can get by clicking this, and what it does, it actually shows you the sun moving around the ecliptic. I'm actually going to do this view. You can see the Earth moving around the sun, which is what we consider, but really what happens is that the sun moves around the ecliptic and the Earth moves around the sun. But if we take a look at it on this side, we've got a person. They're experiencing sunlight, and as we actually get closer and closer to June, which I'm going to stop at when it tells me it's the summer solstice, I think it tells me. Well, it's right about there. If you take a look, if you're standing on the Tropic of Cancer, which is up there, this is the Tropic of Capricorn, there's the equator, there's the Arctic Circle and the Antarctic Circle. This is the first day of summer, and if you notice, if you're standing in the Tropic of Cancer, sun rays are coming almost directly down. So you're getting as much direct sunlight as you're going to get, and this is why we call this the summer solstice. It's a summer for the northern hemisphere. If you watch the Earth as it rotates, if you're in the Arctic Circle, you get 24 hours of lit up sky. You get 24 hours of darkness. But if I slide you up, notice that even when you're up at the North Pole, it's not very much direct sunlight. It's coming off at an angle, so it never gets as warm up there as it does down there. If you go to the equator, notice that it's directly above where the sun is hitting. It's not as directly above, but it's still pretty darn close. In fact, if we actually move the sun around, if you notice at the equator, it really almost always either close to vertical or almost vertical if you look at this up here. And I can move this guy anywhere we want between the North Pole and the South Pole, and you can see total darkness, very little direct sunlight, total direct sunlight, almost direct sunlight. It doesn't have us on this planet because it's not rotating. This is actually coming from, I think, the Great Britain, but I'm not sure why they don't have them in the middle. But this is a neat thing to actually look at, but it's all controlled by where the Earth is in its orbit. Okay, first drawing. What I would like you to do is I'd like you to draw this picture of the atmosphere. These are the layers that I want you to know. Here's a verbal set of them that I'd also like you guys to get. Troposphere, more gas down below, very little gas up there. This is why we need to actually, the percentages of nitrogen 79, oxygen 21 holds true as we go up, but there's less and less gas in the atmosphere. So even though the percentage of oxygen is the same up here, there's less molecules. So when you inhale, you're not getting enough oxygen, which is why anytime we're above 10,000 feet, which is probably about right there, we're supposed to have a supplemental oxygen supply. Actually, the top of Mount Everest, you got to have it too, because you're not getting as much oxygen. Percentage-wise, you're getting it, but you're not getting as much in terms of the molecular value that you're inhaling. These are the layers, and the reason these layers are here are all because of temperature change. And if you take a look at this line, it says as you go up in the troposphere, you actually drop temperature. It gets colder and colder, and minus 60 degrees Celsius or minus 76 degrees Fahrenheit, really cold up there. At that, we call that the tropopause, and that's the last area where the troposphere actually drops temperature, because when we get into the stratosphere, you start seeing the temperature goes up again, and it gets up to close to where zero is, but it's still frozen. And it gets colder again. The coldest area in our atmosphere is actually like minus 80, minus 85, 90 up here at the mesopause, at the top of the mesosphere. And then we go to thermosphere, and then the thermopause, and then the exosphere, which is up here. So closest to the Earth where we live, it's where the weather is, it's where the airplanes fly, and it's actually where all the topography of the planet, whether it's ocean or the highest mountain, all fits inside. Up here we have the ozone layer. That's the area that's actually being destroyed by chlorofluorocarbons, which is allowing more ultraviolet radiation to get in. And then we go up to the mesosphere, the middle sphere. This is the coldest area. Meteorites break down. This is where we actually see the shooting stars up there too. Hopefully they don't get much lower than that. They get vaporized up there. Thermosphere, named after the high temperature, or at least the high energy. Not many molecules to give you high temperature, but it actually gets warmer as we go up. And then the exosphere, this is where the satellites orbit the Earth, and they orbit up there because there's very little material for it to run into and slow down. It fades into space and beyond 300 miles above the Earth's surface, so really far up there. So I'd like you to draw this diagram. I'd like you to include the names, the pauses, which are the area where the layer below it ends. I'd actually like you to put relative altitude up there, like if you put somewhere a little above 10, a little right around 50, right around 85, and then millibars. This is actually 1,000 millibars is sea level pressure, and then you can see there's 1/10 of that, and there's 1/100th of it, and there's 1,000th of it. If you got up to this point, you'd have 1,000th of the air pressing on you, and what happens is voids like lungs, eyes, sinuses all start to expand, and if the bones and the muscles and the tendons can't hold them up, you'd actually find yourself exploding. Neat little effect. Atmosphere, troposphere, the bottom layer. Nitrogen, molecular nitrogen, 79% of the air you're breathing, 21% molecular oxygen, argon, less than 1%, water vapor, carbon dioxide, particulates, all the other stuff that's in there. Temperature decreases as we go up, and there's the temperature as we go up. Warm air is less dense than cold air, that's why warm air rises. Moist air is less dense than dry air, so that's why we get the clouds up here and no clouds down there. And the wind always blows from high pressure, where air starts to sink, and moves up in low pressure, where it cools and condenses and makes clouds. There's the gaseous atmosphere, 79% nitrogen, molecular nitrogen, 21% molecular oxygen, and that's for the troposphere, stratosphere, and the mesosphere, although the number of molecules you see there would actually decrease. Coriolis effect, this is a deflection of the motion caused by the rotation of the Earth. It's important for any objects that move along the surface over long distances, like air, water, airplanes. It does not affect cars, because cars are stuck to the ground. It doesn't affect you because you're stuck to the ground. Maximum deflection of the Coriolis is at the poles. It's almost negligible at the equator. In other words, the Coriolis effect almost doesn't work. This is an animation, and if we actually look at if we had a stagnant Earth and we shot a rocket or a cannonball from the North Pole towards the equator, it would go in a nice straight line. And when I hit this thing, this will be a Coriolis. I'm using a 1-hour flight of a rocket traveling from the North Pole to the equator. As the Earth actually moves, it's 24,000 miles around, so it moves at about 1,000 miles an hour. And if we take a look, the line that it draws is still going to be nice and straight. It moves straight down that line, but the line it draws on the Earth is curved, and that's a Coriolis effect. Effect, not affect. It doesn't really happen, but if you're on the planet, it actually looks like it is, and I'll show it again. Arrow's going straight down. It still hits in the middle, but it actually finds out that it's 15 degrees farther to the west. It's to the right in the northern hemisphere. It's to the left in the southern hemisphere. Atmospheric circulation, it's going to start moving. and it's going to produce these cells, and I'll show that more to you in a shockwave, but I would like you guys to draw this picture. I'm going to give these names, and I'm going to give those names and these names that I'd like you to add, but basically the Hadley cell is the one that actually happens between the equator and about 30 degrees up in both hemispheres, and what's happening is the air is moving down toward the equator, and where it actually converges, it moves up, and as it moves up it makes clouds, and as it makes clouds it rains, and this is why we have a tropical rainforest along here. And then it moves over this way and it starts to sink at about 30 degrees north and 30 degrees south, fed in by the Ferrel cell, which is starting at 60 degrees and coming down, and when air comes down it dries, and this is where we find the deserts. Low pressure center here, high pressure center there. So we have moist air rising at the equator, and we also have it rising up here at about 60 degrees, and while we have the nice rain here in Virginia, where we get 40 to 50 inches of rain a year, and we get the forests of Europe and Asia and North America, and actually the same thing down here, but although there's not many land masses. Southern South America and southern part of Australia, and where we actually, Indonesia is going to be in this equator. It's called the International, what's ITC? I don't remember. It'll come to me. Cool dry air sinks at about 30 degrees north and 30 degrees south. There's cool air sinking there. There's cool air sinking there. This is the polar region where we get basically dry poles, and that's a little hard to understand with all the snow there. But if we actually had as much rain at the poles as we do at the equator, we'd find out that the oceans would empty out, and all the snow, we'd have miles and miles of snow at both of these hemispheres. And I would like you to draw this and label it with equator, subtropical, and polar regions, as well as the Hadley, the Ferrel, and the polar cells for both hemispheres. Surface winds flow from high pressure to low, so where we actually had all these lows, intertropical convergence zone. We have what are called the equatorial doldrums, and we have the horse latitudes, named after all the horses that died at this part. Where the air actually sinks, the boats were not moving very much, and they wanted to get rid of weight. They didn't want to get rid of people or water or the things they were carrying, and they realized that we did need the horses, and lots of horses got dumped overboard. For a while they got tied up to the boat, but it's also shark infested water, and the horses actually either got tired and drowned or they got attacked by sharks. But that's why they're called horse latitudes. And then the polar easterlies are there. These are actually going to be called the trade winds. They're called the northeast trade winds, which I'd like to add to your diagram because they're coming from the northeast. These are the southeast trades because they're coming out of the southeast. These are called the southwesterlies. These are where we live, located right there, and why our weather comes from the west. And these are the northwesterlies, this same sort of thing down here, although again the southern hemisphere doesn't have as many land masses. And then we have the polar easterlies because they're coming from the pole out of the east, and we have the polar easterlies up there. This is the north polar easterlies, and these are the south polar easterlies because they're coming from the south. So I'd like you to add those things to your diagram. This is going to show it to you ideally. So an idealized Hadley cell is going to rise at the equator and sink about 30 degrees. It's going to make clouds, and it's going to make lots of rain. The equatorial regions, it's going to come back down and make a desert, like for Mexico, Arizona, New Mexico. All that area right there is a desert type environment. Throw in the stylized Coriolis effect to the right in the northern hemisphere and to the left for the southern hemisphere to give you the northeast trades, to give you the southwesterlies, to give you the northwesterlies, the southeast trades. Develop more cold air coming from the poles, warmer air moving up there. It's going to start rising up there as well, and we're also going to get these jets. We have what's called the polar jet, and we have the ITCZ, the intertropical convergence zone. And these are where we actually get these storms, these lows to move across. If this thing during the winter, as we actually shift up, this moves farther south, and this is determining our cold air that we get from Canada, whether it be in the teens or the single digits, versus the warmer air we get from the Gulf of Mexico, which may gives us 50 degrees in the winter, and why we actually get the nice humid, really warm air during the summer, and then every once in a while we get a Canadian air mass coming down which cools us down into the 70s for the summer. So if you take a look, this is the whole idea that I showed you before with all the wind masses. The Hadley cell, it doesn't really give you the Ferrel cell up there, but as you can see, this thing rises up and comes back down. So it rises up there and comes back down, and then the polar, which would actually come back down so it can float back down into there. So there's the polar jet, there's the subtropical jet. So during the summer when this thing gets farther north from us, we're going to get all this moist, humid air coming out of the Gulf, and as it dips back down, we're going to get a nice cool air from the north. Surface winds, trade winds, are located between the equator and about 30 degrees. The northeast trades in the northern hemisphere, the southeast trades in the southern. Then we have the westerlies, which I told you before was the southwesterlies or the northwesterlies, depending on where they come. And then we have the polar easterlies up there. And again, you should have this diagram drawn from a couple slides ago. If we didn't have land masses and we didn't have the tilt of the earth and we didn't have seasons and we didn't have land and water and we didn't have one hemisphere being more land than water and the other one actually being less land than water, we'd have a very idealized three-cell model, but because we have all this stuff, it's really complicated. Plus we also have monsoons. Monsoon means wind of Asia and the Indian Ocean, where the wind either comes off the land and it dries the land, or it comes off the water and brings up moisture. It's unequal distribution of land and water, differences of the heat, and if you ever jump from the daytime, if you jump from land into like a pool, there's a big difference between air temperature and water temperature, and if you do the same thing at ground, which we'll talk about with land and sea breezes right here. We have what are called local winds. If you live in the valleys of the Appalachia or the Rockies or the Himalayas, you actually understand mountain breezes and valley breezes, but since this is an oceanography class, we're going to talk about sea breezes, where it actually comes, and air is always named by where it originates. So those southeast trades come from the southeast. The northeast trades come from the northeast. The southwesterlies or the northwesterlies or the north polars or polarlies or polaries or the southeast polars actually are named after where they're coming. So we actually get this wind coming off the ocean. It's called a sea breeze. We get this air coming off land. It's called a land breeze. And I think I'm actually going to show that to you on the next one. We also have what's called sea fog, where the air actually moves off of land and moves onto a warmer, especially at night, moves onto a warmer body of water, and it condenses and makes sea fog. Or we have radiation fog, where the land actually cools off, especially during the evening. The land cools off and we may get condensation there as it reaches dew point. Here is a sea breeze, and it's called a sea breeze because it comes off of the water, and the reason it comes off the water is because the land heats up more, and if you take a look at the land temperature, it looks like it's 20 degrees warmer than the ocean, which is why we like to go in the ocean during the daytime. And if we actually move through time, you notice the sun starts to drop. Notice the wind decreases because the air temperature is getting closer and closer to the same, and when it actually gets to be 65, basically the wind shuts down. And then as the sun sets, pretty soon the water temperature, which is not getting cooler, is now warmer than the air temperature, which is getting cooler, and now we're going to start getting air moving circulation wise, moving this way and coming off the land onto the ocean, which is called a land breeze. And then as the sun comes up, shuts down again, and then starts heating up the land, and we start getting a sea breeze. And that's it. That's where I'm stopping today. So you guys should actually know about land and sea breezes. You should know about why we don't have that three-cell model with the Hadley, the Ferrel, and the polar cells are not perfect because of tilt of the earth, which gives us seasons, because land and water heat differently, because we have a land hemisphere, the northern hemisphere, which is still mostly water, but it's a lot more land than the ocean hemisphere, which is the southern hemisphere. And we have monsoons where it actually changes wind direction. And then you should have all the stuff about global winds, starting with this one and moving with the names of all of it. And again, wind is named by where it originates. So this is coming out of the north, but it's also coming out of the east. So this is the northeast trades. This is the southeast trades. This is the southwesterly. There's the northwesterly. These are the southeast polars, and these are the southeast east, northeast polars, southeast polars, all named by where the wind originates. Coriolis effect, and how it actually is caused by the rotation of the Earth, and it's an observed effect. It doesn't really happen. Atmosphere, the troposphere, diagram of the layers with its temperature, and also noting specifics for each of the spheres. How the season actually changes the amount of direct solar radiation. Albedo, the amount it bounces off. Polar atmosphere, a lot more air to absorb the heat than it is up by the poles. And unequal heating due to latitude. And the fact that the ocean is like a body of water, and so is the atmosphere with waves and changes. Okay, thank you much. Bye.